Now, Archimedes' principle basically said that if you have an object immersed in a fluid, the upward force on that is equal to the weight of the fluid displaced by the object. And the way supposedly that Archimedes figured this out was he filled up the bathtub, he got in the bathtub, and he saw that the level of the water rose when he got in the bathtub, and supposedly he came up with this Archimedes principle, and he ran around, jumped out of the bathtub, running around, yelling, "Eureka, Eureka, I figured it out," and ran around without putting his clothes on. So it's kind of a funny story. But the formula for Archimedes' principle basically says that the buoyant force, again, that's going to be in newtons because forces are in newtons, is equal to the density of the fluid times the volume times G. We all know G. And that's Archimedes' principle. So if we want to solve Archimedes' principle, so if we want to use Archimedes' principle to calculate something, we can just, this is a practice problem. So a cubic decimeter, which is 1 times 10 to the negative 3 meters cubed, of a granite building block is submerged in water. This will be important. The density of the granite is 2.7 times 10 to the 3 kilograms times meters cubed. And they want the magnitude of the buoyant force acting on the block. Okay, so this is our volume. This is the density of the granite. And this is our buoyant force. Okay, so I'm going to write what I know. I know that my volume is 1 times 10 to the negative 3 meters cubed. I know that the density of my object is 2.7 times 10 to the 3. I don't know my buoyant force, but I'm going to find it. Okay, now let's write our formula. Our formula says that the buoyant force is equal to the density of the fluid times the volume times G. Now, they told us that our object was submerged in water. So I'm going to go ahead and I'm going to give you the density of the water, and you could just look this up. That's just what I did. 1,000 kilograms times meters cubed. If they want you to solve something like this on a test, they'll obviously give you the density of the water. And then G. We know this, so add this. Okay, so now I'm going to put the density of my fluid in here. 1,000 kilograms over meters cubed times the volume, which is 1 times 10 to the negative 3 meters cubed times G. Okay, our meters cubed cross out. And then we have kilograms times meters per second squared, which, if you remember, those are the, that's basically newtons. And so our answer is going to be in newtons, which is good because forces are in newtons. And so then we have 1,000 times 1 times 10 to the negative 3 times 9.8. And if you put that in your calculator, you're just going to get 9.8. So your buoyant force is going to be 9.8 newtons. The next thing they ask you, they have the exact same thing, but then they ask you the apparent weight of the object. And so your apparent weight is just going to be your weight, your normal weight, minus your buoyant force and that's going to give you your F apparent. Okay, so we found the buoyant force. I'm just going to do FB, and that's 9.8 meters per second squared. Or, excuse me, I'm so used to putting these units after 9.8. It's actually 9.8 newtons. And then we have the density of our object, which is 2.7 times 10 to the 3. Our volume is still 1 times 10 to the negative 3. And G is still going to be 9.8. So in order to find its normal weight, we just have, we're just going to take the density of the granite times the volume times G. So that'll be 2.7 times 10 to the 3 kilograms times meters cubed. And you can see all I did was I put the density of the granite here instead of the density of the fluid. Okay, same formula. Then I'm going to have my volume. And then I'll have 9.8 meters per second squared. If you multiply these two together, you just get 2.7 times 9.8, which is 26.46 newtons. Okay, now to find my apparent weight, I take this normal weight. This is what the object weighs on land, minus the buoyant force, and its apparent weight is 16.66. This is why when you bring heavy things into water, it feels a lot less heavy, or you feel like you can lift things that you in water that you couldn't otherwise lift. It's because of this buoyant force is making it feel like it weighs less.